Hello everyone. In this video, we are going to talk about the important topic of stress concentration, and also we're going to refer to this principle called Saint Venant. So first, let's talk about the Saint Venant. What is this? It says, if you apply a local load, a concentrated load anywhere on the body, and if you have a basically transducer or any way that you can look at the stress distribution inside the material, like some people use x-rays or other methods to visualize the stress distribution, you'll see that the stress inside the part right under the load is not uniform. So if this material has width of B and thickness of T, clearly right under the load, the average stress is not going to be the same as the average, which is P over BT. If you look at it, right under the load, there is more stress. As you get away from that, your stress drops. So some parts, the stress is more than the average P over BT, some parts is less than that. But as you get away from this concentrated load, you are going to see that the stress gets closer and closer to a uniform distribution. If you do finite element analysis also, you're going to see something very similar. And I'm going to run a simple finite element analysis in SolidWorks and show you that even with when you use FEA and numerical solution, you're going to get this kind of variable distribution near the load, but as you get toward the center of the object, you get closer to uniform. Now, one thing is, how far should you move away from this localized force so your distribution gets close to uniform? Saint Venant principle says as much as a distance as much as the width of the bar. So if this guy is width of B, if you get a distance B away from it, then you should start to see the uniform distribution. Okay, or in general, we call it the maximum dimension of the loading area. So if the loading area is a little bit different size, different dimension, you might need to move a little bit further. But in general, something's equivalent to the width of this beam that is under the load, or rod in this case. You move away and you see the uniform distribution of load, okay, or stress. Now, this is for the cases that the material has uniform geometry. The material has uniform geometry. The geometry does not change. You are going to get to the uniform distribution of stress. But sometimes there are some stuff inside the part or the material or the geometry that we call them stress raisers. These are typically sudden changes in geometry. That is the most common thing. Like what? Like a hole. So there is a hole in the middle of the part, okay? Or there is a sudden drop in dimension like a shoulder or anything like that, okay? So if you have shoulders in 2D or in this case 3D, or holes in the material, if there are grooves, if there are keyways, if there are threads and notches, anything like that, any abrupt or sudden change in geometry, they will cause the stress locally around that sudden change to go up. So that sudden change is what we call a stress raiser, and that sudden increase in the average stress to something much bigger, which we might call sigma max, that is called stress concentration. Okay? So there are two questions here. One is why this happens. Second thing, how much will the stress go up? Because what we need to design the part for is the sigma max. We cannot design for the sigma average or sigma norm anymore, because this number exists inside the material, and when we design, we have to design based on this maximum sigma. So we have to know the relation between maximum sigma and the average sigma. This relation is a parameter, we call it the stress concentration factor, or K, which depends on the geometry, and I'm going to talk about it in a second. But first question is why this happens in the first place. So there are a bunch of different explanations for it, and the one that is the most common one, and I like the most, to be honest with you, is basically is called disruption of stress flow. So, and it's very similar to fluid flow. Okay, if you have some, consider this like a cross section of a pipe, and inside that there is this kind of object that is obstructing. When the water starts flowing in, well, they have no problem until they reach this obstacle. Now, what should they do? They should go around it, correct? They cannot pass through it. They should go around it. So what would you get? You get congestions here. It's like the traffic of the cars in streets where there is some obstacle in the middle of a street, right? You see some lanes are closed. You're going to get congestions. And when you're going to get congestions, what happens? The traffic slows down and it will be disrupted. The same thing applies for stress. When you apply some loads on this material and axially loaded, the stress ideally likes to be uniform. But when there is this hole, there will be no stress in this cavity, so the stress lines or the force lines will have to curve around this sudden change in geometry, and that is causing congestion, and that is causing a raise in the stress. Okay? That's why if you have sharp features like sharp internal edges like that, in order to reduce the congestion and the stress concentration, what I always say to my students, if there is an internal edge, you always fillet that. When you fillet that, now they have a little bit more room to basically more gradually go from this bigger area to this smaller area. So if you have a shoulder with a sharp edge, make sure you fillet it. It will release some of the stress concentration. It will definitely bring it down as opposed to being perfect sharp like that. Okay, and I'm going to show you in the stress concentration plots. The smaller this number is and go to 0, the bigger the K value is going to be. So fillet is what? Very, very important for internal edges. So that is the best explanation that I like about the stress concentration. Now the question is, how much does it go up? Well, that depends on the geometry, depends on what kind of geometry you have and what kind of sudden change in it. So for different kind of changes in geometry, we have different plots like this that are all acquired experimentally. So for instance, if you have a 2D plate and it's under axial load and there is a hole in it, the height of the plate is B, the diameter of the hole is D, and it's exactly in the middle. You can see that there is, for instance, this K plot versus the ratio D over B. So the bigger the D is compared to B, see what happens. So when D gets bigger and closer to B, ideally to half of it, the K drops. Okay? And you can see, for instance, let's say it's 1/3 of B. So it's here, and then from here you go on to the curve and you read the value, and let's say it is, for instance, 2.35. Okay, so your maximum stress is going to be 2.35 times the average stress. Now the average stress in this case could be P over B times, and let's say the thickness of this material is T, so times that. Okay, so sigma max is clearly in this case K, or 2.35 times that average stress, right? Like this. Okay, and for different geometries, there are different charts, right? These charts are all taken from the book, as I said, Mechanics of Material by Gira and Brooks, which is a really good book. So here you can see for this scenario that you have a shoulder instead of a hole. Now you have two dimensions that are important. One is R over C, the radius of the fillet, divided by the thickness of the second, or the width of the second shoulder, or second part of the shoulder, the smaller part. And the other one is the ratio of B over C. Okay, so per B over C and per R over C, you have to read the data, and then that gives you a K. So now you can see that, first of all, as the R gets smaller and smaller, which is basically going to no fillet, you see that these stress concentrations are all going up. Okay, so if I have no fillet, and I cannot say no fillet because there is always a tool fillet here, but if I have something as 0.05 as opposed to 0.255 for the same B over C, you can clearly see that my stress can go from this number to this number here. Right? So look at that. It is here about 1.6 or less. Here is about 2.3 or 2.25. So you see how much you can spare material and perform better by just increasing the fillet's radius, right? So that is very, very important. And this is also the 3D version of that. So this is a shaft here. It's not a plate, it's a 3D, it's a rotary object. So there is diameter 2, diameter 1, again a radius. And again, it depends on radius over D1 and D2 over D1. And again, you see smaller radius means bigger K factors. In some books, it's shown by KT, concentration factor KT as opposed to K. Now, let's look at one example here. So here we have the step bar. So we clearly have, and there is a hole in it, so we can use this graph. And the dimensions are given as from 9 centimeter, you drop to 6 centimeter. The thickness of the material is 1. The fillet radii are basically 0.5 each, and the whole diameter is 1.8. So you have two stress concentrations here. One is because of the hole, one is because of the fillet. And this material, the maximum stress that it can tolerate, the ultimate strength of it is 200 megapascal. If your safety factor is 2.8, you want to know how much is the maximum load that you can apply. And if you see here, it is going and using the maximum strength as opposed to yield strength. Typically, we use yield strength, not ultimate, because we don't want the material to deform. In this case, maybe they don't care about deformation. All they care is no fracture. So in this case, the sigma allowed is going to be equal to the maximum strength divided by the safety factor, correct? So it is going to be 200 divided by 2.8, and we are going to get 71.43 megapascal. This is the max that this material we want to tolerate. Now, there are two concentration factors that we have to read. One is because of the hole. For hole, we need the number, and the number is, as you just saw, is D over B. Now, in this case, the diameter of this hole, we have the number for it is 1.8, and the width B is 9. So this ratio is going to be 1.8 over 9, which is clearly 0.2, right? 1/5. So we go to 0.2 and we project on the curve and we read, and the stress concentration factor we get, KT number 1, is 2.51. This is what you can have because of the hole. The other one we need to read is because of the fillet radius. This time C is 6, B is 9, and fillet is 0.5. So we can go and look at this graph here this time and remember the numbers that we have. So fillet is 0.5, C is 6, and then B is 9, C is 6, so you get 1.5. So we have to look at the curve that has a value of 1.5, which is this curve, and we have to go over 0.5 over 6, which is less than 0.1. So we come here at around this number, which is about 0.08 or something, and we project it onto this curve. So if we go up straight like this, and we read this straight concentration factor, right here, you can see that the stress concentration is smaller than that. So the number I have is, let's see, that one is about 2.35. So I go down here and I say the second one I have because of the fillet is 2.35. Now, clearly, which one of these would you pick? Well, you always pick the bigger one, because the bigger one is the one that gives you the maximum stress and that will limit your load. So we pick the bigger one, and now we say that sigma maximum is equal to the biggest of this K, which is 2.51 times sigma average or sigma norm. And sigma norm in this material is P over B times T. P is unknown, but B is 9 centimeters and T is 1 centimeter. And so this maximum is this number that you can possibly have. So from here, if you solve, the only unknown is P, and if you solve for P, the load that you are going to get is 18.24 kilonewton. This is the maximum load you can have for this structure with two stress risers, a shoulder, and a hole. And as I promised you, I'm going to show you some small FEA now. Of course, you can see them under my playlist, SolidWorks or ANSYS. You can see that here, this is a simple rod, and I applied the load on it, right? So this side is fixed, this side I pulled. And if you look at this here, look at the 1 minus stress, you can see that, look here, around the location of the fixture, or if you look at the other end, you can see, especially on this fixture size, you see that the stress distribution is not uniform. Now here, this is not a local force I applied it to the whole surface. But if I applied it to a local area on the surface, I would definitely see that the load distribution will not be uniform. But here around the fixture, you clearly see it's not uniform. But as I get away, and let's look at it from the side view, as I get roughly away from the surface by a distance equal to diameter here, about this much, this is where the uniform distribution is all over the place. You see that? So all I need to move away is about diameter, and then I get uniform distribution. And here I changed the load and I applied it to a local feature as opposed to all of it. And again, you can see that right under the load, the distribution is not uniform, but here all you need is to just get a little bit away from it, and you're clearly going to go back to uniform distribution. Okay, so clearly these local things are basically you can get away from them when you move at most a distance of d, in this case, away from that local feature, whether it's a local force or it's a constraint or anything like that, and you can get to uniform distribution. So hopefully the video was useful to you, and I'm gonna see you in the next lecture. Thank you.